In this lecture, let's look at an example of function behavior. Here we want to sketch a graph of a function that satisfies the following characteristics. We want to have a function that has three roots at x equals to -2, 1, and 3. And it has a horizontal asymptote at y equals to -2. And a local minimum at x equals to -1, and a local maximum at x equals to 2. You can pause the video here and try to do the example by yourself, then you can continue the video to check your answer. Note that for this example, we could have different sketch. As long as the behaviors of the graph is the same, then the sketch are all correct. Let's start with the roots. We want to have three roots. One root at -2, one at x equals to 1, and one at x equals to 3. The next property is we want to have a horizontal asymptote at y equals to -2. Suppose here is -2. Then I want my function never pass this dashed horizontal line. Here I draw the horizontal line in the positive x direction, but you could also have a horizontal asymptote on the negative x direction, or both. So in my drawing, as I increasing x, my f of x will get closer and closer to this horizontal line. Then the next property is that we want to have a local minimum at x equals to -1. Let's suppose the function will pass through this point. And it is a local minimum, which means that this point will have a valley shape. Then the last property is that the function has a local maximum at x equals to 2. Suppose the function passes through this point, and we have a local maximum, which means that this point will have a hill shape. Now let's connect the points and draw a function. I want my function to pass through the root. Then it has a local minimum at x equals to -1, and the next root is at x equals to 1. And it has a local maximum at x equals to 2, then the next root is at x equals to 3. And I have a horizontal asymptote at y equals to -2. That means as I increasing x, my function will get closer and closer to this horizontal line. I'll copy the graph from the textbook, since the sketch in the textbook is much better than mine. And in part B, let's approximate the locations of the inflection points on the graph. Remember that inflection point is the point where the concavity changes. If I move from the left, my function decreases until local minimum, then it increases. Over this interval, my function is concave up. Then around this point, my function increases until local maximum. Then it decreases again. So over this interval, the function is concave down. So my inflection point will be around here. Then as we continue to move in positive x direction, we see that the concavity changes again. Here, as the function gets closer and closer to the horizontal line, the function has a U shape. So we change the concavity around here again. So this is another inflection point. So to answer part B, we have inflection points at around x equals to half and at x equals to 4. How about part C? Given the graph that you sketch, find the intervals on which the function is positive, increasing, decreasing, and concave up. Let's start with positive. A function is positive when the function on the graph is above the x-axis. Using the interval notation, f is positive on from -infinity to the first root, -2, and from 1 to 3. So union 1 to 3. Then function is increasing from the local minimum to the local maximum. Using the interval notation, function is increasing on -1 to 2. And the next one, function is decreasing on all the other intervals, which is from negative infinity to negative 1, union from the local maximum 2 to positive infinity. In the last question, function is concave up, on. We've already covered this when we answered part B to find the inflection point. This function is concave up over the interval from negative infinity to the inflection point, half, and from the second inflection point, which is 4, to positive infinity. And that is the end of the lecture. In the next lecture, let's look at an example of average rate of change.